Alright, this is a video to kind of explain where the idea of continuously compound interest comes from. And the basic idea is this. In our normal compound interest formula, if we let the principal equal $1, so you'll notice that in front of our function here we don't have anything in that where that p would normally go. Our rate is also going to equal 100%. Or basically, notice on top of our fraction, we've got an r value equal to 1 in our larger interest formula. And also our time, notice that up in the exponent we don't have a t value, will also be equal to 1. If we let all of that happen and then play around with the n, the compounding number, we're going to watch our numbers sort of flatten out or sort of approach a very important number to mathematics. So first of all, we might want to realize that, again, if you do annual interest, that means we're getting that annual interest one time per year. But again, we're getting 100% interest, essentially saying that we're doubling our money. We're going to keep 100% of our money, but also gain 100% interest, so doubling our money. If n is 1, this becomes 1 plus 1 is 2, and your annual interest basically becomes, I now have $2 in the bank. So if you start with $1 after 1 year getting 100% interest, you double your money. Now, if we earned quarterly interest, on the other hand, not only would we get that extra dollar, we'd double our money, but we're getting that interest 4 times during the year. So rather than having that be 1 up in the exponent, we're getting that 4 times. And again, if we replace n as it being 12, we get it monthly. You'll notice we get a little bit more money every single time. So if it helps us out, if we gain more money by making n larger and larger, chopping up our interest into small amounts, but getting that interest more often, why don't we do that daily or hourly, or even if we could, per minute? So if we do that daily or hourly, notice how our numbers are going up and up. We gained 44 cents, then another about 17 cents, then we gained another 10 cents. Again, this is still in 1 year. The amount of time hasn't changed. We're just doing the work a little more often. We're getting the money 12 times a year, or 365 times a year, or 8,760 times a year. If we do that per minute, again, making those computers in those banks work a little bit faster, we actually gain a little bit more. But notice, not even a full cent anymore. We actually only gained about 2/100ths of a cent. So at some point, getting that number more and more often sort of doesn't pay off anymore, or it sort of tops out. We're not gaining enough money for it to really matter. So if we could chop that year into continuously compound interest, make n into infinity. We're going to get an infinitely small amount of interest, but getting it an infinite number of times. You would actually find out that your number would come out very, very close to, in fact, precisely on, what's called Euler's number, the natural base. We define that as E. So if you ever see E in a problem from here on out, notice we've defined that much like pi is 3.14159 ... going on forever. E is 2.718281828 going on forever. Although it looks like there's somewhat of a pattern, there really isn't. It does infinitely keep going onwards and outwards, changing, a little bit farther down the road. What that helps us do is, instead of taking our compound interest formula being P times 1 plus r over n, we're going to change that into what's called the continuously compound interest formula, or PERT. How PERT can help us is, first of all, looking at what a graph is going to look like, or how that E can help us is looking at what a graph can look like. Much like our growth and decay functions from previous, we just want to quickly define all the various parts of a continuously growing or continuously decaying function. Realize that E, again, being 2.7 approximately, is greater than 1. That makes this function initially a growth function. This one would also be a growth function, but notice here E is to a negative 2x, which means a negative exponent, which means 1 over E to the 2x. Well, if E is greater than 1 but is on the bottom of a fraction, that makes this decay. The asymptote will still be at y equals 0 for any normal growth function. Realize here we've shifted down 2, so y is going to equal negative 2. And realize over here we didn't shift at all again, so y equals 0. The domain, it's still an exponential function, so all of these can still be all real numbers. Having e in the base doesn't change the fact that an exponent can't give you negative numbers, can't give you 0. So our range is still going to be that y is greater than, note that we're a positive 1/8 out in front, greater than the asymptote. Again, a positive 2 out in front here means y is going to be greater than the asymptote. And again, positive 1 in front of this e would mean that y is, again, greater than 0. If you graph any of those three functions on your calculator, you'll quickly notice that they'll look just like all the other growth and decay functions. The only difference is your base is e now, the Euler's number, or that continuously compounding number. Now, how does that help us in the real world? Well, what if we had a bank account that we wanted to continuously earn interest on, or anything where we want to continuously grow or decay? Well, if I want to know the balance of $1,000 at 8% compounded interest, compounded continuously, notice it's still 8% APR, annual interest, right, is an APR, but compounded continuously, I'm not going to use my old continuously compounding formula. I'm going to say that PERT, or basically the principal, times e raised to the RT, so for 5 years, will give me my interest. It'll give me what my bank account will have after, again, 5 years. So if we head on to our calculator very quickly, I'm just going to open up a new document real quick to help us out. We can say that $1,000 e, which if you noticed over here at the left side of your screen, is just a button on your calculator. So we've got e to the power of 5 times our interest rate, which again, if we remind ourselves, was 8%. So 0.08, and multiply that out, we will end up with $1,491.82. 1,491.82 for an amount. Now, PERT typically has more applications to sort of more real-world involvement, more than just bank interest or interest formulas. PERT is more how things would grow in population, because populations don't grow at the end of the month or the end of the day. They're typically going to grow continuously. Or, such as atmospheric pressure, more of a smooth line. There's no jump. You don't just get pressure at 100 feet and 200 feet. There's atmospheric pressure everywhere in between. So we've got a formula here that will give us the atmospheric pressure in PSI, pounds per square inch, given that we are d miles above sea level. So how much pressure per square inch would you experience at the summit of Mount Washington, 6,288 feet above sea level? First thing we need to notice is, yes, we just do want to plug in for d. We want to plug in for that height in order to find the pressure. However, notice they gave us feet in the problem. So 6,288 feet. First thing I need to do is convert that to miles. Well, if feet is on the top of a fraction, in order to cancel it away, I need to put it on the bottom. And remember that there are 5,280 feet in a mile. So we can go on our calculator. 6288 divided by 5280, and we'll get a nice answer, 131 over 110. So I can take that 131 over 110 and plug it into my formula. The pressure will be equal to 14.7 e to the negative 0.21. Notice e to the negative means they're decaying away. So as our d value gets larger, as we move upwards into the air, the pressure is going to be coming down. Or as you move higher in the air, it gets thinner. You have less air pressure going on. That makes sense as far as the science side of things goes. Plug in our d value though, and we'll basically find out that p equals, so 14.7 e. So I'm going to say 14.7 e to the negative 0.21 times, and as long as I've got it on the screen here, I'm just going to go ahead and say times and copy that number directly in there, and we'll end up with 11.447, about 11.447 psi, pounds per square inch, at a height of 6,288 feet above sea level. How about if we wanted to estimate the height above sea level if the pressure is 13.23 psi? Notice they didn't say anything about having to go back to feet, so don't worry about the conversion. I'll be happy to do this in miles. But realize that, again, that means we're saying 13.23 equals 14.7 e to the negative 0.21 d. And again, we don't know quite yet how to solve those equations. If you know how to do that by hand, feel free. Otherwise, let's graph. And from the graph, we can find out what d is. So let's go ahead and head on here. And we'll go to a graphing page. So control the page. And we're going to graph 14.7 e to the negative 0.21 x. Remember, our variable is always x. But then I want to know, when is that going to be equal to, if we remember down here, 13.23. So I'm going to graph a horizontal line at 13.23. Press enter. Notice we don't see that on the screen, so I just need to move my screen up a little bit. And if 13.23 is what we want to reach, I should go to at least probably about 15. You'll notice there's my crossing point right there, my intersection point. So control, don't want control, just menu, analyze graph, intersect. And if I go left bound, right bound, we will find out that at 0.502 or so, at about 0.502, and remember that we are technically operating in miles, we will end up reaching that pressure. Hope that helps you understand exponential growth and decay a little bit more as well, by using it in a continuously compounding, or using that letter E, Euler's number, to help ourselves solve graphs. Good luck, and have a great day.